Okay, so thank you very much for the invitation. And I mean, having grown up mathematically in Bonn, I appreciate especially that Vlad is now assimilated enough to insist on proper German blackboard cleaning technique. So I hope my technique is still up to German standards. So let me start by describing the goal today, and just by comparison, let me recall the Kovacs description of the Neff cone of K3 surfaces. So if SH is a polarized K3 surface, then I mean it's by now classical that the Mori cone is generated by -2 classes. So in other words, it's generated by the positive cone and by all C such that C squared is equal to -2, and the intersection with the polarization is given by is positive, right? And so the goal is something like this for hyperkähler varieties. So let me say we want a hyperkovac result. Okay, and so I mean the setting is that X8 is a polarized irreducible holomorphic symplectic variety.
Are you going to call it a hyperkovac?
Then it'll forever be unclear if you should capitalize it.
Okay, and I'll consider those of K3 types. So of K3 types, in other words, it deforms to a Hilbert scheme of points. To a Hilbert scheme of points on a K3 surface. And we want a result that's comparable like this. So ideally, we would like a description of the Mori cone purely in terms of lattice theoretic data. And I mean, this question was first studied systematically by Hassett and Tschinkel, and they made a conjecture. And so let me describe a little bit about the setup of their conjecture, because in the result is really a variation of what they originally proposed. So of course we have this Bovil-Bogomolov form on H2 of X, and on the Neon-Severi group it's just given by so the pairing of two divisors is given by the integral over X of d1 times d2 times the symplectic form to the n-1 times the complex conjugate. So here where omega is a suitably normalized holomorphic volume form. And I mean it's this is a pairing of signature as one would expect for a surface. So the signature is 1, rho of x minus 1. So it makes sense to talk about the positive cone. And I mean from the Fujiki relation says that the volume of a divisor is governed by this quadratic form. And I mean from this one immediately gets that the Neff cone is contained in the positive cone, just as for K3 surfaces, or dually the dual statement to the Mori cone containing the positive cone. And now, if you look at H lower 2 of X, then of course we can think of this as H upper 2X dual. And if I do all this over Q, then I can use the Bovil-Bogomolov pairing to identify the dual with the space itself. And from this we get a Q-valued Bovil-Bogomolov form on H lower 2. Right, so and this is of course, I mean this makes it even possible to formulate analogous statement. And they propose the following conjecture based on many examples. that the Mori cone is completely determined by this quadratic form. So they suggested that it's generated by the positive cone and by all curve classes, so that C.H is positive and the self-intersection is greater or equal to minus n plus 3 over 2. Yeah, so M2n is the dimension, the complex dimension of X. And let me call this the Hassett-Tschinkel cone. Right, and so I mean for n equal 1 for the K3 case, you would get back the covert statement, but for higher dimension, it's more subtle. And I mean this. And so I mean the result will be that the actual truth is extremely close to this conjecture. Actually, it's true in small dimension, but we'll need a little bit more data. And so I mean, before describing the actual result, let me make some remarks. I mean, of course, dually we would get the Neff cone of X, of course. And then, I mean, the movable cone has essentially been described by Markman. So, I mean, if one takes the positive cone, then he gives a precise description of the boundary walls of the movable cone. And so, I mean, the only parts he didn't describe were the potential boundary points of square 0. And then, I mean, this positive cone has a chamber decomposition into where the chambers correspond the chambers correspond one-to-one to marked birational models. Marked, let me say, minimal models. So in this case, I could just say that Y is smooth and also K-trivial to make this unique. And of course, the decomposition is given by pulling back the Neff cone. Right. So I mean, so in particular, I mean, a result like this would describe this chamber decomposition precisely, and so it would immediately give a list of all birational models of the given variety X. Okay, so let me just. I mean, the actual answer will describe a little bit of setup, which I'm going to explain. Any questions so far? And so, I mean, of course, there is Verbitsky's global Tirelli for hyperkähler varieties, but note that, I mean, if it does not say that, I mean, if I have two such K3 type irreducible holomorphic varieties, simply hyperkähler varieties, then it doesn't automatically follow that they are birational. Right, so I mean the period map, of course it identifies birational models, but even after that it's finite to 1. And it only identifies this if the isomorphism is given by a monodromy transformation. And so in the case of varieties of K3 type, Markman has made this extremely precise. I mean, to what extent this strong global Tirelli fails. And so, I mean, his description is given in terms of an extension of hot structures. So H2 of X embeds into a hot structure of rank 1 bigger. So this is an extension of integral polarized weight 2 Hodge structures. And so, I mean, moreover, there exists a V, a primitive vector, so that such that the, I mean, this H2 is just the orthogonal complement, and V squared is equal to 2n minus 2. Again, 2n is the complex dimension. And, I mean, the key point why this extension is useful is the following. So, on the one hand, the monodromy action extends. So this extends to an action on lambda x twiddle. And moreover, that's really, I mean, that really exactly describes monodromy transformations. And then, I mean, together with the precise statement of global Terrelli, it then follows that the x is birational to x prime if and only if there is an Hodge isometry. So from lambda x twiddle to lambda x prime twiddle, that sends plus minus v to plus minus v prime. Right, so the statement is that, I mean, to rephrase the statement is that an Hodge isometry comes from a monodromy transformation if and only if it extends to an Hodge isometry of the slightly bigger lattice. Okay, so and I mean, moreover, in the case when we consider Hilbert's scheme or a modular space of sheaves, then this lattice is exactly what one would think it is. So okay, so I mean, as a lattice, this lambda x twiddle is just isomorphic to the Macri lattice of a K3. And so let's say we start with a K3 surface, and I pick an algebraic class. And now I consider of the right self-intersection with respect to the Macri pairing. And then if I set x to be equal to the Giesecke moduli space, so here where H is a polarization, or I mean, or it's a moduli space of Birational stable objects. So sigma is a Birational stability condition on X, and then M sigma of V is the moduli space of Birational stable objects. I mean, then in this case, I mean, there is the Hodge structure of X is completely determined in terms of the one on S, and that's a result by well, by Yoshioka, but based really on earlier work. But, it says that, I mean, there's an isomorphism from the orthogonal complement of V inside the cohomology to H2 of X. Okay, and so the statement is that here Markman's inclusion of Hodge structures is just the inverse of this one. Okay, and so I mean, this is, I mean, how is this morphism given? I mean, for algebraic classes, it can be constructed as a determinant line bundle on here, so it gives an algebraic class. And in general, it's induced by the, I mean, the Chern character, or more precisely, the Mukai vector of the universal family that exists. Okay. Okay, and so the actual answer is that this is really the data that we need to describe the Mori cone. Okay, so I mean, if I look at this theta from V perp and now inside this lambda x twiddle to h2 of x, then I mean dually this gives, so here in general I just define theta to be the inverse of I. Then dually this gives a morphism from this lattice modulo V, so V is always an algebraic class, to h2 of x. Okay, and now the actual statement is that this is the data we need to describe the Mori cone. So if xh is as before, then the Mori cone of x is generated by the positive cone and by all classes, sorry, I wanted to call this theta V or theta dual. So by all classes theta V of A, where A is of the following form, so it has to be square at least minus 2. It's, if I take the pairing bit A, that has to be at most V squared over 2. And of course, the pairing with the given polarization has to be positive to pick out whether I'm using plus or minus A. Okay, so that's the claim is that this is the Mori cone. Any questions on the statement? Sorry? Yeah, so it's easy. It's easy to see that any such class satisfies the Hassett-Tschinkel inequality. So in other words, so the Néron-Severi group, the Mori cone is always contained in this Hassett-Tschinkel cone. And moreover, I mean, and actually more precisely, I mean, moreover, each extreme array contains an effective curve class, or not just an integral class in the cohomology. So an effective curve class C with C comma C greater or equal to minus n plus 3 over 2. I mean, basically, it's easy to compute the. I mean, from this condition, it's easy to compute the self-pairing of A after I project down to V perp, and that's the same as the C comma C. And so let me give the attribution of this theorem. So So for for the case where X is a Giesecke moduli space or a Birational moduli space. And this is due to my work with Emmanuel and Macri. I'll say a little bit about this in a second. And then, I mean, deforming from this case to the general case, this so this was done by Giovanni Mongardi using twisted deformations and independently by in a paper by myself with Hassett and Tschinkel, using deformation theory of extremal curves. Okay, so let me say a little bit about part A. But then the main part of the talk today will be about part B. I mean, this is, as I said, this is based on wall crossing for Birational stability conditions. And so the idea is the following. So I mean, there's this manifold of Birational stability conditions. So I mean, here let me talk about the case x equal m sigma of V. And so in particular, I mean, this includes the other case of a Giesecke moduli space, because I can always arrange my stability conditions so that the stable objects are exactly Giesecke stable sheaves. And so I mean, in this Birational manifold, there is a chamber decomposition. So sigma is contained in a chamber, so when sigma varies within here, the moduli space doesn't change. And then here at the walls, we get some strictly semi-stable objects. And the moduli space changes. And so let me set B equal to V minus A. And I mean, these conditions are actually symmetric with respect to A and B. So in particular, they are almost symmetric. I mean, B squared is also at least minus 2. And I mean, then there exists a wall WA in the space of Birational stability condition where, I mean, the slope of objects of class A is equal to slope of objects of class V is equal to slope of objects of class B. And let me make a assume that this wall is actually a wall of this. I mean, this could be a wall out here. And so let me exclude this case. Let me assume that it's really a wall bounding the chamber containing sigma. So this borders the chamber containing sigma. And I mean, incidentally, this is actually equivalent to R being extremal rather than effective. And I mean, the picture is that somehow these dimension conditions, A squared greater equal to minus 2 and B squared greater equal to minus 2, guarantee that the corresponding moduli spaces are non-empty. So I can pick objects in here, and let me also pick here a stability condition on the wall. And I mean, then it's a simple numerical argument that there are always extensions from B to A. So the extensions A into E onto B, so these always exist, and then it's actually also not a difficult argument to show that these produces stable objects of class V. So this gives a projective space inside this moduli space. And moreover, I mean, the wall actually contracts this moduli space. So if I look at the morphism from the moduli space of stable sheaves for sigma on the chamber to the coarse moduli space of semi-stable objects for the stability condition on the wall, then this contracts this projective space. And in particular, so one can really control a lot about the geometry here. I mean, I can control, for example, I can control the sigma 0 is a stability condition on the wall. So, for example, I mean the class of the line in this projective space is exactly given by theta v of a. And yeah, I mean, one can really control the geometry of this contraction quite a bit in terms of the lattice associated to the wall. I mean, once I have this condition, then of course any class that's a linear combination of A and B automatically also has the same slope, and this will give me additional irreducible components of the exceptional locus of this contraction. So it's really, I mean, the geometry is really nicely controlled by wall crossing, as one could hope. Okay, any questions at this point? Yeah, I mean, it can vary in the moduli space. So it's a PR bundle, and I mean this PR bundle can degenerate into something reducible if there are also objects in, say, M sigma of A that become strictly semi-stable. But I mean, it's also easy to construct example where this contraction has, say, arbitrarily many irreducible or connected components in the exceptional locus. Okay, so but I mean, today I want to focus more on the deformation argument, and it's so as I said, there's this independent argument by Mongardi using twistor deformation, but our argument instead uses, I mean, a deformation theory of extremal rational curves. And of course, global theoretic happening.
Sorry, so what is case B then?
Sorry?
What is case B? Maybe you wrote it, but maybe I missed it.
I mean, just the general case. Sorry. I mean,
Oh.
So of the deformation type of Hilbert scheme of points. Okay, so assume that R is extremal, and that so pi from x to y is the associated contraction. And let me pick let E be an irreducible component of the exceptional locus. So of the exceptional locus of pi. And then let me also be S be a generic fiber of this morphism, so of pi restricted to E. And then, I mean, first of all, the F is rationally connected. And I guess the right reference for this is Macri. And now let's pick a minimal rational curve that connects two generic points in F. So F from pi 1 to F of minimal degree. So such that, deformations of F connect two generic points of F. And then of course one can use bend and break arguments for this family. And so this is, I think one should cite Kebikos here and Chow, Miyoka, Shepard, Baron to determine the normal bundle, or let's say the pullback of the tangent bundle. And really the crucial part is that it has only one factor of O of 2. So this part is due to bend and break, and then the self-duality of Tx then guarantees that the negative part has one factor of O of minus 2, and then a number of factors of O of minus 1. Okay, and this is really somehow this is essentially the hard part, and the rest after that is more or less easy. So this means that the dimension of the deformation space inside the space of morphisms from P1 to X has dimension 2m plus 1. And from this it's an actually a fairly easy argument due to Rahn that with F as above, if I have such a rational curve with this normal bundle, then F of C remains effective along deformations of X where the class of C, so this extreme array, remains algebraic. And of course, this is sort of a semi-regularity statement that we have only one obstruction given by this O of minus 2, and this obstruction isn't realized among deformations where R remains algebraic, but in fact the actual argument is much simpler than that. Just so proof, consider a deformation. So X goes to 0. Let's deform this along a curve. So B curve along which R remains algebraic. And now let's extend this to a two-parameter deformation. So that the curve is no longer algebraic along the general point of C, so that R not algebraic over general point of C. And now if you look at the space of morphisms from P1 to xc that contains f, then I mean the dimension is at least equal to the expected dimension, which is the dimension of xc. So this is 2n plus 2, which is greater than the dimension of the space of morphisms to x. Right, I mean bigger than this deformation of f inside x. Right, and so I mean just by dimension reasons there must be deformations along B. Otherwise the space couldn't have dimension 2n plus 2. Okay, and so I mean this lemma almost already implies that the Mori cone is at least as big as claimed. So one just needs a little bit of one more monodromy argument, and I mean this actually again uses essentially a result by Markman on the movable cone. So this shows that the Mori cone contains these classes. So then, right, I mean, of course, the idea is to deform X to a Hilbert scheme where we know that this class is effective. And if you could also assume that this class is extremal, then we would be done. And this can be done by changing the monodromy and going to a different birational model. Okay, so I mean the reverse inclusion is based on the following observation, namely that if R is extremal and X to B is a deformation of X, and let's say B is a quasi-projective curve, and R remains algebraic, then I mean we know that R remains effective, but even moreover one can show that R is extremal away from finitely many points. Right, so I mean, why is this a non-trivial statement? Of course, because the dimension of H11 jumps at infinitely many points, but only finitely many of them can cause R to cease being extreme. Okay, so I mean, this is one ingredient, and then the second ingredient is really, I mean, a small lemma. Oh. I mean, somehow an easy consequence of global Torelli. This is in a paper by Rocha and Markman. That I mean, let me just say that these moduli spaces of rich and stable objects, they are sufficiently dense in the moduli space of such varieties of K3 type varieties. Right, so I mean, of course, it becomes a hot theoretic decomposition. And then one can construct, I mean, starting with an X and an extreme array, one can construct such a deformation so that infinitely many points in this projective curve are isomorphic to a moduli space of rich and stable objects on some K3 surfaces. Okay, so I mean, this basically completes the proof. So I'll finish with some remarks. Any questions? So I mean, I guess one natural question is to ask whether the same strategy works for comma type varieties coming from abelian surfaces, and the answer is I don't know. So I mean, again, for moduli spaces of stable sheaves or Birational stable complexes, the Mori cone is described. So this is in work by Yoshioka and collaborators. But I mean, some of the equivalent of Markman's description of the monodromy action is not known to my knowledge. And so, as far as I can tell, this case is open in general. And but let me also say that I mean, basically a similar strategy works for the existence of Lagrangian fibrations. And I mean, there the so the statement is that so if we have x as above, and let's say we have an integral divisor in the Neon-Severi group of square 0, then x is birational to a Lagrangian fibration. And I mean, this was proved for x equal m sigma of v's again by myself and Emmanuel Macri. And in slightly different generality, so actually for a very general variety of this type, by Markman, and then a deformation argument extending this to all varieties of deformation of this deformation class by Markman. This was proved by Matsushita. And I mean, how does this proof work? So this proof works by, I mean, basically showing that if I start with such a m sigma of v, so where this is a Birational stability condition on a K3 surface S, and this is a vector v, and then I mean, somehow this class pair 0 divisor class gives me a different K3 surface that is derived equivalent to my different K3 surface that is derived equivalent to my original one. And then here we use wall crossing to reduce it to the case where it's well known, where I have a Giesecker moduli space of sheaves of rank 0 and supported in some curve class C and S. And of course here, I mean, here I have the support map, right? So this always has a map to the linear system associated to C, given by the Bouville, or called the Bouville integrable system. And again, note that these are dense in the moduli space. So so in this construction, the generic fiber here are Lagrangians, right? The generic fiber is when I have a smooth curve, then the fiber will be a Picard variety of this curve. A line bundle of a certain degree, and the role of stability is to say how the degrees split up and my curve becomes reducible. Right, and since this is true in a dense set, it actually follows that the fibers are always Lagrangians. But I mean, I don't feel like this is a satisfactory explanation. I mean, there must be a nicer explanation for this, why these are always Lagrangians. Okay, let me stop here, since I don't know the answer.
Thank you very much for your talk. Are there questions?
So, with the description of the Mori code and also the dual code, can you control sort of what kind of MMPs I can run, or can I always run MMPs
I mean, yes, certainly yes. I mean, actually, I mean, certainly for movable boundary, it's already in the papers by Hassett and Tschinkel. And yeah, I don't think there's, and then, I mean, if you have a fixed point locus, you have Zariski decomposition. I don't think there's any, I mean, I don't think this is due to us. I mean, of course, so, I mean, for these modulations of friction stable objects, you can run any MMP, at least for movable boundary, just by changing the stability condition. But I don't think this, yeah, I don't think this needs our methods.
Then we thank you